In this video, we're going to look at applications of Taylor polynomials. And the reason for that is many students ask the completely reasonable question, if we have a function like y equals e to the x, and our calculator can compute e to the x apparently quite easily, why would we ever trade that in for the overly simplistic linear approximation like y is approximately, e to the x is approximately 1 plus x? We can do it, but why are we doing it? We're going to see a bit of this through this video series, but I just want you to know in terms of the bigger context that this idea of Taylor approximations to functions like e to the x, these transcendental functions, and other ideas like this, turning a complicated function into a series of simpler building blocks, that's also done with something called Fourier transforms and Fourier series. These in applied math are just as important as the idea of the derivative itself or the integral. This idea of taking a function and breaking it into a series and looking for structure in those series is an incredibly powerful tool. We will dip our toe into that zone, into that area, but just know that there's a lot more that goes on beyond this. For now, let's see if we can find some questions that we were not able to answer earlier that now we could answer with the help of Taylor polynomials. Here's our first example. Evaluate the limit as x approaches 0 of e to the negative 2x minus 1 over x. So the first thing we should do is try to sub in. You never know if this is continuous. If we try to plug in x equals 0, maybe it works. Of course, it's not going to be that easy, but let's see why. E to the 0 minus 1. Already we have a problem in the denominator, and we actually have a problem in both the numerator and denominator in the sense that this is an indeterminate form. And remember, an indeterminate form means you have to go back and do more work. This ratio doesn't have any meaning at all. You have to go and simplify the original expression somehow before you can evaluate the limit. But there's a problem with that, which is this is not the kinds of formulas we've seen before. This is not a polynomial over a polynomial function. So we can't do some of the tips or tricks that we used before, like dividing by the highest power. This is not going to work because we have a polynomial on the bottom, but we have an exponential where the x is in the exponent in the numerator. So literally none of the tools we've seen up until now can assist us with this problem. Enter Taylor polynomials. If we take this e to the negative 2x, and notice that we really want to know what's happening around x equals 0, so what we're going to do is build a Taylor polynomial for e to the negative 2x and get a really good approximation for that around x equals 0. All right, let's call that our function. We'll try the quadratic and see if that's enough. We'll take the derivative, negative 2, e to the negative 2x. Get a second derivative. That will be a negative 2 again, so it'll be plus 4 e to the negative 2x. We need all of these evaluated at x equals 0. F of 0 would be e to the 0 is 1. F prime of 0, using this formula, we'll have negative 2 times e to the 0, which is 1, so just negative 2. And last but not least, we have 4 e to the negative 2x for e to the 0. That's just going to be 4. What does that tell us? Well, it means that e to the negative 2x can be approximated by a polynomial, p2 of x, which is defined by our function, 1, plus the slope, negative 2, times x minus 0, plus the 4 over 2 x minus 0 squared. This is the quadratic Taylor approximation formula, f of a, f prime of a, x minus a, plus the quadratic derivative, second derivative, divided by 2 times the quadratic term, x minus a squared. This is our generic formula for a degree 2 or quadratic Taylor polynomial. Just filling in the blanks here for the specific function. So how does that help us? Well, let's tidy this up a little bit. We have 1 minus 2x plus 2x squared. That is what we can use to approximate e to the negative 2x. So we have the limit as x approaches 0 of e to the negative 2x minus 1 all over x. We can replace that with, I'll write approximately here just because we are using an approximation in our statement, but I'll talk about that in a moment. We can replace the e to the negative 2x with 1 minus 2x plus 2x squareds. That is our replacement for e to the negative 2x. We still have the negative 1 out front, and all of that over x. Oh, well, that gives us some options now. This time we can cancel some of the terms. We can ask what happens as x goes to 0 when we have negative 2x plus 2x squared. I'm just going to erase this content here so we have a bit more room. We have negative 2x plus 2x squared all over x. Well, that we can definitely simplify. The x and 1x from each term in the numerator cancels with the denominator x. Now we have simplified our expression down to the point where we can sub in again and hopefully get a better result than we did initially. If we sub in x equals 0 into this, out pops our limit, negative 2. And so starting from this complicated exponential form and getting an indeterminate form that we had no tools to work with, what Taylor polynomials let us do is sub out this transcendental function that we couldn't really work with or cancel or simplify and replace it with a nice polynomial. And the polynomial stuff is much easier to cancel, simplify, work with. And after we did that simplification, we get down to a nice simple value for the limit because we can just sub in. We don't have this 0 over 0 problem once we've done that simplification. But what about the approximation issue? There's a lot of theory that would go into this and behind the scenes. But if you remember what the roots of this Taylor polynomial construction is, we start off with a complicated function and approximate it with a polynomial. But remember that those are actually perfectly equal to each other at x equals 0 in this case. These two things are identical, have the same properties at the point where we build the approximation. It's only an approximation as you move away. And so if we're taking our limit exactly towards that point, we can conclude that we're going to get an equal sign here. That is a very hand-wavy argument. We will not ask you to make that kind of logical construction because it takes a lot more proof work to make that convincing. But at the end of the day, the point that we're approaching is exactly the point where this approximation is best. And so the most suited for swapping out the complicated initial function with its approximation. So it is a valid way to approach these problems. Let's take a look at a second example to reinforce those ideas. The limit as x approaches 0 of sine of 5x over x. Again, we'll try the naive subbing in approach. And we'll see that we get a problem fairly quickly, which is sine of 0 is 0. And as x approaches 0, x approaches 0. That is, again, an indeterminate form. So we have to do more work. We first note that this is not a rational function. This is not a polynomial over a polynomial. So our earlier techniques of canceling or dividing by the highest power of x definitely will not work here. So what do we do instead? What we can do is build a Taylor polynomial for sine of 5x. And we want to build it where this approximation is helpful. We're going to build it at x equals 0. So here we have our sine of 5x. Let's call it g of x for this page. We used f of x last page. We'll build a quadratic again and just see if that's enough. We'll need the first and second derivatives to do that. Oh, we have to be a bit careful here though. It was sine of 5x. And so when we differentiate sine of 5x, we get cos of 5x back. The derivative of the inside is 5 though. So we get a multiplier of 5. And then when we differentiate the cos, we get negative sine of the same thing with the 5 out front. And then we get another 5 from the derivative of the inside. So we'll have negative 25 sine of 5x's. At the point x equals 0, that's going to simplify to g of 0 is Sine of 0 is 0. G prime of 0 is going to be 5 times cos of 0, which is 5 times 1. And the second derivative may not be too useful here because it is also going to be 0. Sine of 0 is 0. All right, so that means that we can replace sine of 5x as a good approximation around the point x equals 0 with 0 plus 5x minus zeros, and we have the second derivative. I'll put in all the details just to reinforce the structure, but none of that's going to matter because this 0 multiplier wipes it all out. And so what we really have is 5x. Well, that lets us evaluate the limit though, I think. If we ask what happens as x approaches 0 to sine of 5x over x, well, that's going to be the same thing that happens to not sine of 5x, but its excellent approximation, 5x itself, over x. And of course, we can cancel the x's there. And then we have the limit. You have to be a little bit careful here that you don't over-cancel in your mind. What happens as x approaches 0 to the number 5? Well, the number 5 doesn't care about x too much, so we just get the number 5 back. And so the limit we're looking for here has a value of 5. Now, some students might be looking at that last example in particular and thinking, I've seen something like this before. It feels like these ratios with limits has been covered by other tools. That is very possibly the case. L'Hopital's rule is a rule related to Taylor polynomials. It's actually built based on Taylor polynomials, but it's a sort of simplified and streamlined way to do what we just did in that last example. We're going to see that in the upcoming videos.